Now that we know about metric measurements, let's take a second to look at accuracy, precision, scientific notation, and significant figures. Now we've completed our review of scientific notation, significant figures, and significant figures in measurement. Let's now concentrate on density, percent error. For the most common mathematical problems in chemistry, we're going to refer to our equation sheet found on reference table T. This is the very last page of our reference table. At the top of reference table T, we're given the density calculation. So they tell us that density is equal to mass divided by volume. We're also given the percent error calculation. When calculating both density and percent error, you may need to use reference table S as a reference. Reference table S gives the density of many common elements. Again, density is defined as the mass per unit volume. So in this case, mass is determined by the number of atoms. So in the picture to the left, we have 20 atoms, and in the picture to the right, we have 5 atoms. Now, we can see that the picture to the left is approximately 4 times the picture to the right. So we could say that this would be, if this is 1 unit, the volume, and then this would be 4 units. Notice that if we simplify our fractions, they have the exact same density. Density is a feature called an intensive property. What makes density an intensive property is that it is constant regardless of the amount of matter, whether or not you have 4 units or 1 unit. It is constant. So this explains why a popsicle stick floats on water, as well as a boat made out of a large piece of wood, the same type of wood that a popsicle stick would be made out of. Now let's take a look back at our review sheet. The first question asks us to round this number to 3 significant digits. So looking at the number, the first important thing is to identify which digits are significant. I will be applying the Pacific rule as there's a decimal present, so as written, this number has 5 significant digits. If I only want 3 significant digits, what I'll do is I'll underline the digits and I'll circle the next digit that will determine whether or not I stay at this number or if I round up. Since this digit is a 0, I'm going to stay at this digit. So this number would be written as 0.410. This number only has 3 significant digits. Choice B is our best choice. The next question is a percent error question. So the important part in this question is to identify what numbers we're going to use in percent error. We're going to use this 10 grams of solute per liter of solution, and we're also going to use 8.90 grams of solute per liter of solution. Now, in the percent error question found on reference table T, we know it is our measured value minus our accepted value over our accepted value times 100. So the hard part here is, in the question, it doesn't say accepted value or measured value. But remember, whatever is done in a lab, whatever a student does or you do, that is always going to be the measured value. And whatever is expected is usually what is accepted. So here, since the student intended to make a solution that is 10 grams of solute per milliliter of solution, this is going to be our accepted value, while the value that the student actually measured, 8.90, is going to be the measured value. So to calculate the percent error, we're going to take 8.90 minus 10 divided by 10 times 100. Of course, order of operations applies here, so make sure that we calculate the numerator before dividing by the denominator and multiplying times 100. When we place this problem in our calculator, we see that choice C is the best answer. In the next problem, again, we can see that it is a percent error question. Now, this problem says show the correct numerical setup, so we'll want to show all of our math here. Now, there are two numbers in this question that concern us. There is the accepted mass for acetylsalicylic acid, which is 325 milligrams, and there is the determined mass of 320. Recall that reference table T says that the equation for percent error is measured minus accepted divided by accepted times 100. So in this case, our measured value is 320, our accepted value is 325, and we're going to go and divide that by 325 and multiply times 100. Now here is the calculator result from my calculator. This is not the answer that I'm going to go and report because it's not to the correct number of significant digits. The number 325 obviously has 3 significant digits, while the number 320 also has 3 significant digits. It has 3 significant digits because in the question we can see that there's a decimal present. So we'll approach the number from the Pacific side. Now the rules for assigning significant digits, we'll have to go back and take this step by step. So the first mathematical operation we will perform is a subtraction. In addition and subtraction, we're going to have our answer have the same number of decimal places as our problem. And then we have a multiplication and division. In multiplication and division, our final answer can have no more significant digits than in the question. Since every number in this question has 3 significant digits, I'm going to round my number to 3 significant digits. I'm going to keep 3 digits, and I have to look to the next digit, the 4th digit, to figure out rounding. So the number I'll report is negative 1.54%. With percent error, you can report it as either it's positive or a negative. Sometimes absolute value is reported, and sometimes the true value with the sign is given. This negative value means that my measured value was less than the accepted value. Finally, let's do this graphing activity together. So here we see that we have a cooling curve for stearic acid. First thing we're asked to do is mark an appropriate scale on the y-axis. So to mark an appropriate scale, we have to look at what numbers are given on our y-axis. Numbers here are between 75 and 65. That has a range of 10. So I'll write that down just to help me later on. Now, what many students may wish to do is to make their scale so that every number from 0 to the top number is displayed. That actually is not the best graphing technique, as we're really only concerned with the numbers given. In chemistry, our scales do not have to begin with the origin 0, 0, but what is not allowed is a line break. So you cannot go and signify this to be 65 and every other tick to be 1. So that'd be 65, 66, 67, 68, 69, and then we'd mark this as 70. This is not appropriate because this says that this tick has a measurement essentially of 65 because 0 to 65, while every other tick only has a tick of 1. So this is entirely incorrect. So what do we do instead is we're going to go and make an appropriate scale beginning with our lowest number. So if we make 65 this bottom number, then we can go and designate each value as 1, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75. Whenever graphing, you want to make sure that your actual graph takes up at least 75% of the provided graphing area. So I've plotted all of the data from our data table, and now what I'll need to do is I'll need to circle the connected dots, and actually connect my dots. Finally, for states of matter, we know that we have these 3 major states of matter that we're going to focus on in chemistry, and you need to be familiar with all of this information, including shape, volume, particle movement, density, intermolecular forces, and particle diagram. I'm not going to review them because I think they're very clearly placed here in the diagram, but if you need to, pause the video to make sure that you are familiar with these things. The only thing I'm going to focus on is particle movement. Remember that in the solid, particles vibrate in fixed position. In the liquid, the particles are very tightly packed together, but they're able to slide past one another. And in gases, the particles are in this constant random straight line motion. Now let's look at a few practice problems. Here we're looking for a gas in a closed container. So we recall that gases take the shape and completely fill their containers. So in this case, this choice B, is the best choice. Choice C shows a solid because it has its own shape and it has its own volume. Choice D is a liquid because it is taking the shape of the container, but it still has a unique volume because it's not completely filling the container. The next question asks, given the particle diagram, which element could this represent? So they give us a couple key points. First of all, they're giving us the pressure, which is related to STP, so that's actually fairly insignificant. And they're giving a temperature of 298 Kelvin. So in order to answer this question, we're going to refer to reference table S. Reference table S gives us melting point and boiling point data for all of these elements. Now we'll have to compare that melting point and boiling point data to the given number, which is 298. Looking at reference table S, we're going to want to use melting point and boiling point data to determine the state of the substance. Now remember that when using this data, which can be found here, we're going to essentially make a number line. The number line is going to include the melting point and the boiling point. If your number of interest falls before the melting point and boiling point in a number line, then it will be a solid. If it falls in between the melting and boiling point, it will be a liquid. And if it falls after the melting and boiling point, it will be a gas. So if we use krypton as the example, and recall that the given number was 298, we have the numbers 116 and 120. The number 298 falls to after the boiling point. That makes krypton a gas. So it is best to mark a result on your test before you continue going and looking at other elements. The other elements are found on the next section of reference table S. Let's continue with silver. Silver is element number 47. We can see that the melting point is 1,235. So if we're going to make this a number line, our number given, again 298, would fall to the left of the number line. Since it's falling to the left of the number line, that's going to make silver a solid. Again, remember that it goes solid, liquid, gas. Now when we look at xenon, we can accomplish the same task. We see that the melting point is 161 and the boiling point is 165. So the number 298, if this were a number line, would fall to the right of the boiling point. So because of this, this xenon is a gas. And lastly, we have radon. Radon has a melting point of 202 and a boiling point of 211, so the number 298 are going to fall to the left of the number line, making radon a gas. Let's go back to our question. So here we've placed the state of matter of all of our elements, so we can see that our best choice is going to be silver, one because it's different, and two because the particle diagram has a regular geometric pattern consistent with solids. On the next question, we were asked which particles are arranged in a regular geometric pattern, which again describes solids. So the formula isn't relevant here. The only thing that is important is the symbol for solid. So choice C is the best answer. In this final question, we are asked to draw the particle diagram of nitrogen, a diatomic element, in both gas and liquid form. So we know that in gas form, the particles are going to be very far spread apart, versus in a liquid form, the particles are going to be very close together. Also notice that I'm using the box as a container. So liquids in a container, they have their unique volume, but they take the shape of the container. So I'm showing that the particles here are not completely filling the box, but they're very close together. So they have their own volume, but they are filling the bottom portion of the box, meaning they're taking the shape of the box. It asks, describe in terms of particle arrangement the difference between nitrogen gas and liquid nitrogen. In nitrogen gas, the particles are in constant random motion and they are very far apart, whereas in a liquid state, the particles are extremely close together and they can slide past one another. The last question asks, good models should reflect the true nature of a concept being represented. What is the limitation of a two-dimensional model? One of the biggest limitations of two-dimensional models is they don't show movement, which are really important when describing the behavior of gases and liquids. That concludes the review for Test 2. Good luck!